Okay, so I'm recording again. Good. Okay, so this is the practice. These are the practice problems for the final. And so we're going over this. Again, the final is 1 hour long, 10 questions, each worth 10 points. Okay, these are only practice problems for the final. The final will be different. So anyone have questions about any of these 10 practice problems for the final? You may be waiting to do these problems until after this exam, which makes sense. So I don't know. Here's what I'm going to do. I'm going to go over a lot of these problems. You may want to do these problems yourself without seeing. Okay, I'll go over question 9. We're going to go over a bunch of these problems. If you want to do the problems first without seeing the solutions, you could leave this Zoom meeting and then watch this video online where I go over the solutions. Though you won't be able to ask questions about it. And remember, I'm telling people whether or not I received their final, whether or not I received the test 2 answers at 12:05. Okay. Oh wow, it's already 11:34. Okay, so you know what? I'm going to now ask people. Does anyone want me to? If anyone cannot make it at 12:05 p.m., does anyone want me to check whether or not I received their exam answers?
Professor, did you receive mine? Yes, if you can, please.
Okay. So one at a time, and I didn't have the video in front of me. So someone asked me again. Just say who you are when you ask, so I can.
Oh yeah, my name's Charlie. And
Oh, I see you. Okay, Charlie. Yeah. Sure, Charlie Gomez. Okay. Your exam.
I wasn't. I forgot for the first page has the first 3 questions because I forgot that you wanted it to be on different pages for each question.
Okay, so I see that. So I see 1, 2, and 3.
Yeah.
And then for 3, it's A, B, and they have 4, and then you have number 5. I have all 5, and I have the file. You're good.
Okay, good. Yeah.
Okay.
Thank you.
Anyone else? This is if you cannot make it at 12:05. Ayesha Siddiqui, you said you can't make it at 12:05. Yeah, so I'm assuming you can't make it at 12:05. So this is Ayesha.
Professor, did you get mine?
Okay, so I'm saying Ayesha because she said if possible me. So it's just I'm going by what I see first. So just give me a second. Question 1, question 2, question 3, question 4, question 5. So okay, Ayesha, I have your entire exam and I have 5 answers in one email. Good. 1, 2, 3, 4, 5. Okay, good. Next, MST Muna, you said you asked?
Yes.
Okay.
Yes. Okay, so I have 1, 2, 3, 4, and 5. I have all 5. You're good. Okay, anyone else?
Yes, me. Homer Body.
Sure. Okay, Homer Body. Okay. Okay, I have all 5, Homer Body. I have all 5 of your answers. Okay, anyone else who can't make it at 12:05 want me to check whether I received their entire exam?
Can you check mine's Sunny Nguyen?
Sunny? Sure. Okay. 1, 2, 3, 4, and 5. I have all 5.
Thank you.
You're welcome. Okay, anyone else?
Professor, can you check mine?
Okay, can't make it 12:05. Okay, Jia Yang Yu. Okay.
Yeah.
Professor, could you check mine as well?
Oh, one at a time. 1, 2, 3, 4, and 5. Jia Yang,
Yeah.
I have all 5 of yours. Okay, who's next?
Last name?
Hasnain, sure. Hold on. Okay, it's out of order. 3, 4, 5, 1, 2. Okay, that's all 5. 1, 2, 3, 4, and 5. Hasnain, I have all 5.
Okay.
Anyone else?
Professor, can you please check mine?
Sure, who's this?
Mashior.
Sure. Mashior, you said?
Yeah.
Oh, there you go. I see you. Okay. There's like a yellow bar that goes around the video when someone speaks. No, I was looking for it. Okay, Mashior. Good. 1, 2, 3, 4, and 5. Yep, I have all 5.
Okay.
Good. Okay. Jilin. Okay. This is for people who can't make it at 12:05.
Professor, can you also check mine?
Okay, hold on one more time. Jilin. Good. 1, 5, 4, 3, 2, and every picture is sideways. 1, 5, 4, 3, and 2. I have all 5 of your answers sideways in separate sheets of paper. Okay, Jilin, I have your entire exam. Okay, good. When you send the exams, try to make it so it's vertical, not sideways. Okay, but you sent it now. Okay, good. Who else wants me to check their exam?
Yeah, can you check mine?
Ahmed, okay.
Yes.
One, 2, 3, 4, and 5. I have all 5 Ahmed of your exam answers. Okay, anyone else can't make it at 12:05? Want me to check?
So can you check mine?
Okay, Sabrina, okay. Okay, I have all 5 of your answers on separate sheets of paper. Very good. Okay, good. Thank you. Anyone else?
My name is Haseeb.
Claudia?
Check mine.
Claudia? Okay, Claudia Carranza Garcia. Claudia. One, 2, 3, 4, and 5. I have all 5 of yours separate sheet paper. You're good, Claudia. You're good too. It's like I'm doing an auction where I talk really fast. Okay, anyone else have another? Want me to check? Anyone else? You can't make it at 12:05?
Mine, Professor Marusha.
Marusha, okay. I accidentally clicked your email before, so I'm glad you asked because now all the ones I've looked at are the ones I've checked. Okay, so 1, 2, 3, 4, and 5. I have all 5.
Mine, Adrian.
Marusha, you don't have to cut off the pages so that it's only the space that you use. I guess that's nice. You have it cut off so that it's not wasting space. It's fine to leave the whole page. I don't know if it's a problem. You could do it the way you did it, but if you have the whole page, it's easier for me because then when each page is a different size, it's a little bit weirder to see on the screen. I'm being a little particular though. You can do it that way too. Who else wants me to?
Adrian.
Adrian, okay. Adrian Medina. One, 3, 4, 5. Wait. Oh, this is number 2. Okay, the way you wrote, is your second page number 2?
Yeah.
Okay, you see how you have like a second parentheses on the left side?
Yeah.
Okay, but that's number 2, right?
Let me just double check. Yeah. That's number 2. Sorry.
Okay, it's okay. I'm checking just because that was a little weird. Okay, so don't do that and then final. Okay, so you have
Yeah.
1, 2, 3, 4, and 5. I have all 5 of your answers. You're good.
Okay.
Anyone else? Okay, so everyone else can make it 12:05, you're saying, right? Okay. Hassan, I don't know why the yellow bar is around. I think you might have spoken. briefly, and then the bar is still on. But okay, so you don't have questions. Okay, good. Okay, so now
Professor, did you get
let's
mine?
talk about the final. Okay. So okay, remember this is due at 12:05. Okay, so I think this is already on the screen this whole time. So these are the practice problems for the final. If you wrote in the chat something about the final, please resend it because I've now gotten like 20 messages since then. Someone said question 9. I saw that, but then there's been lots of messages since. Okay, so if you ask something in the chat about practice problems for the final, re-ask your question now. Okay, I've answered all like 20 messages about sending exams, but I haven't addressed this yet. Okay, so so let's look at number 9. So for number 9, it says if the variance of 3x plus 5 equals 18, find the variance of x, right? Okay, so I'm thinking variant when I see variance. Okay, so then, okay, so this is number 9 and not number 1. I don't know what it's doing. Okay, so if the variance of 3x plus 5 is 18, find the variance of x. So remember, this is a fact that the variance of ax plus b is equal to a squared times the variance of x, right? So, so you can just apply this formula to this situation. And so in the problem, you have the variance, you have that here, you have that a is equal to 3, b is equal to 5. Okay, and so that means by the above fact, we have that the variance of 3x plus 5 is equal to a squared, which is 3 squared, times the variance of x. The value of b doesn't make any difference, but I wrote there just anyway. Not equals 9 times the variance of x. So you see that the variance of 3x plus 5 is equal to 9 times the variance of x. Now we're given that the variance of 3x plus 5 is 18. So sometimes people will put the 18 on the right side, just for because they. But I'm going to do this way so the equal sign makes complete sense. So 18 is equal to this, and then this is equal to that. Okay, so we have that the variance of 9 times the variance of x is equal to 18. And so now you just solve for the variance of x, and you get that the variance of x is equal to 2. Make sense? It says 18 or divide by 9, which is 2. Okay, so I think they answered your question. I just turned that off for a second because I want to go to the just want to get another file here. There we go, good. Okay, so on Blackboard, right? You have the answers to review problems for final here, right? If you click the test link and then you click the final link, you can click this, and these are the answers. Those are the problems, and these are the answers. If you click the answer sheet, you'll get this file, right? You may not want to see the answers right now. Number 9, there it is, right? So variance of 3x plus 5 is 9 variance of x. And then the variance of x is equal to 2 because that's 18. And then you solve for variance of x, you get 2. Okay, so that's number 9. Okay, so you can see how that relates with what I wrote here. I'm giving a little bit more of an explanation here. Okay, anyone have other questions about other problems on the sheet? Other than question 9? Okay, let's look at the sheet for a second. So let's look at number 4. Find the probability of getting at least 3 heads in 10 tosses of a fair coin. Okay, so number 4 is find the probability of getting at least 3 heads in 10 tosses of a fair coin. Now I'm going to just check. Find the probability of getting at least 3 heads in 10 tosses of a fair coin. Yep, that's it. Good. Okay, so let's do this one. Okay, so I'm just going to write here solution. I'm going to write here solution. And I am recording. Good. Okay, so we're going to use the binomial probability function, right? So let capital X be, so let a Bernoulli trial be the act of flipping a fair coin. Let a success in each Bernoulli trial be flipping heads. Flipping the coin on the heads side, facing up. Okay, so we have a Bernoulli trial, each flip of the coin, and we have a success as being flipping the coin heads, getting heads, right? So little n, which is the number of Bernoulli trials, is equal to 10. Little p, which is the probability of success in each Bernoulli trial, well, that's equal to the probability of flipping heads, right? That's equal to the probability of heads, and that's equal to 1/2. As a decimal, that's 0.5, right? And so, and then little x is going to be the number of successes, right? That will be a variable that will change depending on which value of the binomial probability function we want. So the problem is asking us to find the probability of and so it actually capital X, good. Capital X is going to be the number of heads you flip in 10 coin tosses. Okay, so X is the number of heads. Okay, so each simple outcome is 10 flips of the coin, and then X takes that simple outcome and then spits out the number of heads in those 10 flips. Okay, so the probability of at least 3 heads in 10 coin flips, that's equal to the probability that X, the number of heads that you flip, is at least 3, right? And so that means that, not at least, so it's greater than or equal to 3. So probably at least 3 heads in 10 coin flips is the probability that the number of heads X is greater than or equal to 3. Okay, and then that's equal to, well, that's equal to 1. That's equal to 1 minus the probability that X is not greater than 3, meaning it's less than 3. And the probability that X is less than 3, well, what are the possible number of heads that are less than 3? You could either have 0 heads, you could have 1, you could have 2. Okay, so the probability of X less than 3 is the probability X equals 0 plus probability X equals 1 plus probability X equals 2. And you take that sum, entire sum, and you subtract it from 1, because that's the probability of less than 3, X less than 3, that you're subtracting from 1. And so this is equal to 1 minus the sum in brackets. And so you just need to calculate each of those probabilities and plug them in. Well, the probability that X equals 0 is the value of the binomial probability function, where the number of successes is 0 heads, in 10 Bernoulli trials, where the probability of success is 0.5 or 1/2. And so that is the value of that binomial probability function, is the probability that there are 0 successes in 10 Bernoulli trials, where probability of success in each Bernoulli trial is 1/2. Okay, that's plus the probability that there's exactly 1 heads in 10 coin flips. That means there's 1 success in 10 Bernoulli trials, where the probability of success in each Bernoulli trial is 0.5 or 1/2. Then it's plus the value of binomial probability function when you have 2 successes, because you want 2 heads for P of x equals 2 in 10 Bernoulli trials, where the probability of success in each Bernoulli trial is 0.5. Okay, so you're taking the sum of those 3 values of the binomial probability function, and you're taking that sum, you're subtracting the entire sum from 1. And then that's the answer, right? And so now you just need to calculate each of those things, plug them in, and then 1 minus that sum, and then do the arithmetic. This is equal to 1 minus the sum, where b of 0, 10.5 is the same. You calculate that as there we go. That's the same as 10 to 0 times 0.5, the probability of success raised to the 0 power, because there's 0 successes, times 0.5, the probability of failure, 1 minus 0.5 raised to the 10th power, for 10 failures. Then that's plus, for b of 1, 10.5, this is 10c1 of 0.5 raised to the 1st power, 1 success, times 0.5 raised to the 9th power, 9 failures. 1 minus 0.5 is 0.5. That's plus then 10c2. This is for b of 2, 10.5. That's 10c2 times 0.5, the probability of success squared, times 0.5 raised to the 8th power for 8 failures. Okay, and so it's 1 minus that sum, and that will give you the answer. And this is equal to, and I'm just going to put as a reminder, the binomial, I'm not going to put reminder, I'm going to put fact. Okay, fact, right? B of x colon n comma p is equal to, this is the formula, right, for the binomial probability function. And you have n choose x, and then you have p, the probability of success raised to the x power, times 1 minus p, or q, 1 minus p raised to the n minus x power. Okay, and so that's the formula that you can use to get each of these values for these 3. And if these 3 have these 3 corresponding values, using this formula. Okay, and understanding the formulas, it helps you remember the formula. Okay, I'm not actually, I'm not recalling this formula. I'm just knowing the formula because I understand the function. If you understand the function, it's much easier to remember the formula. Okay, so then, so for number 4, you have 0.945. So when you calculate that, you get 0.945. That's equal to 0.945. And there you go. So that's the answer to number 4, because that's the one I said let's go over. So that's number 4. Okay, anyone have questions about some of the other problems? Okay, so for number 6, it says if the P of A is 0.2, P of B is 0.5, P of A union B is 0.6, find the probability of A prime, B prime, and probability of AB. So I'm going to copy this. This is number 6. So I'm going to go now to Word again. Let's look at number 6. That's number 6, and it says find those 2. Okay, so we're going to find those 2. So now the solution is that you want to find each of these things. So look at the whiteboard. Okay, for this problem. Okay, so we're going to go to the whiteboard. And so for the problem, actually, I'm going to go back to, I don't know whether or not, let's see if you can, I'm going to copy this and paste it into the whiteboard, but you have the file, right? You have the file and this, and so you can have it in front of you instead of here, but there it is. Okay, so so this is number 6. Okay, so number 6 in review sheet for final. Okay, so if P of A is 0.2, P of B is 0.5, P of A and B is 0.6, find the probability of A prime, B prime, and probability of AB. So that's the probability of A prime, B prime. Okay, the caret means that it's just, right, ignore it, there's no caret here. Can I write over this? Nope. That's A prime, B prime. Okay, forget the caret here. It's just A prime, B prime. Okay, we want the probability of A prime, B prime. Do it by hand. There we go. Okay, good. So let's do this. Okay, so okay, so if you have your universal sets, well, what are the sample space? Okay, and then you have P of A is 0.2. So let's go with orange. So P of A is 0.2. So this is set A. You don't have, there's no need to use colors on the exam. I'm just doing it here to help the lesson. You have B here, there. Okay, so you have set A and B, right? P of A is 0.2, P of B is 0.5, P of A union B is 0.6, right? So what you need here is remember the formula? So you actually, maybe the Venn diagram isn't even what you need, but A union B, that's A union B. That's equal to 1 minus left. Probably A union B is P of A plus P of B minus P of AB. Okay, and so what that means is that P of A union B is 0.6, right? So 0.6 is equal to P of A, which is 0.2, plus P of B, which is 0.5, minus P of AB, A intersection B. Okay, so that implies, this implies P of AB is equal to 0.1, right? You just solve for P of AB of 0.6 equals 0.7 minus P of AB, and so that means P of AB is 0.1. So P of A and B is 0.1, and so we've already solved this first one, right? We're good here. We found P of AB is 0.1. But now here, P of AB is 0.1, and so that means the probability in this intersection is 0.1. Well, if the intersection is 0.1 and A is 0.2, that means that this is another 0.1 here, only in A and not in B. And if this is 0.1 and the probability B is 0.5, that means the probability in B and not in A is 0.4. And so now you have these. Now P of A prime B prime is equal to, so P of A prime B prime means not in A and not in B. Well, if it's 0.456, there's 0.6 in A or B. So that means outside the circle, that has to be the remainder, which is 0.4, because this adds up to 0.6 and outside of it is 0.4. And so that means that the probability of A prime B prime, which means not in A and not in B, which is the same as the complement of A union B, this is the same as the probability of A union B prime. And the only reason I'm writing is A union B prime is just so you can see it's outside of A union B. A union B is those circles, right? So A union B is everything I'm underlining in light blue, right? That's A union B. Right. So that's A union B, right? A union B is that, and so A union B prime is outside of that, what's not blue, and so that's 0.4. And so you get 0.4 as your answer. Probability of A prime B prime is 0.4. And there's the answer. And so that's also done. It's also now also done, right? So this is done here, and this one was done here. There we go. All right, and so that's number 6. And so that's completely explained right there. So that's number 6. Let's look at the whiteboard for the complete solution and explanation to this problem. Okay, so that's number 6. Okay, so let's look at the review sheet again. Okay, so I went over a few. Okay, number 10. How many ways can 8 books be arranged on a shelf? And how many ways can 8 books be arranged on a shelf? Okay, and how many ways can 8 books be arranged on a shelf? And so for this one, I think you have, right, it's right here. So if you have 8 books arranged on a shelf, why not? Let's go on the whiteboard and I'll draw it. Okay. Okay, so if you have a bookshelf and you have 8 books. Okay, so if you have a bookshelf, which I'm going to make brown for bookshelf, and you have 8 books in the bookshelf. Okay, so you have 1, you have a book here, 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 book here, you have a book here. They could be different sizes, I guess. 6. You have a book here, 4, 7, and then there's one more, and let's put there's an orange book here. Okay, so you have 8 books there. You want to arrange them on a shelf, right? But it doesn't have to be in this order. You can rearrange the order. And so when you arrange these books, you have 8 spots where they can go. I'm gonna use black. So you have 1, 2, 3, 4, 5, 6, 7, 8. Right. So what book do you want to put in the first spot? You can put the blue one, the red one, the purple one, the light green one, brown, light blue, dark green, or orange. You have 8 choices. So there are 8 choices for which book goes in the leftmost spot in the arrangement on the shelf, right? And so then after you put one of these 8 in that spot, there's then 7 left to go in the second spot. And then after you chose that one, there's only 6 left to go in the third. And then there's only 5 left in the fourth. Then there's only 5 left in the fourth. Then there's only 4 left after that. Then there's only 3 left for the next spot. Then only 2 left for the next spot. And then only 1 left for the next spot. These are the number of choices you have for each spot in the bookshelf. And then in order to find the total number of ways to make all those choices, you just multiply the number of ways to make each choice. Right, that's the multiplication principle. So by the multiplication principle, the product of these numbers is the same as the number of choices you have on that bookshelf. And that's equal to, right, 8 factorial. That is 8 factorial, but then you multiply it out. And so if you multiply this out, I just want to make sure I don't make a mistake here. It's 40,320, 40,320. And so 40,320. Okay, that's 40,320. This is number 10 on the review sheet. All right, any questions about this? That makes sense, right? Okay, so that's number 6 on the review sheet right here. That's number 6, and this is that's number 6. This is number 10. It's a blank one that I would like to get rid of, but I don't know. Okay, so that's that. Let me just quickly go back here. So the complete solution. Look at the whiteboard for the complete solution and explanation of this problem. Let's just make this the same. Okay. Okay, so now I will go over with you whether or not you received your whether or not I received your test answers. So okay, ask me. Anyone just say out loud if you want me to check whether I received your. It's now due.
Professor, can you check mine? Ima?
I'm sure. One, two, three, 4, and 5. I have all 5 yours. You're good. I am.
Thank you.
You're welcome. Okay, so the final review is done now, unless people have more questions.
Can you check mine?
Sure. Okay, so yeah, after I check your exam, you can go. If people have more questions, so I will still talk. So if you want to be sure, you can just stay and wait also. Who just asked?
Saba.
Who?
Saba. Saba Minhaj.
Saba. Okay. Saba. One, 2, 3, 4, 5. Okay, I have all 5. Saba, you're good. You know what I'm gonna do? Instead of asking me, I'm just gonna assume all of you want it to be checked. I'm gonna randomly just whatever I see in front of me. I'm gonna say a name, and if you want me to check, say here. Hassan Meliani. Do you want me to check? Hassan Meliani.
Hello?
Hi. Yeah. Okay. So I'm gonna tell you. I have 1. You did them out of order on the same page. I have 1, 3, 2, 4, and 5. 5, 4, 3, 2, 1. I have all 5 of yours. Hassan, you're good. Kashan Shah. If you're here, I don't see Kashan Shah here. I may be wrong. I don't see that. I don't see him here. Okay, so oh, okay. Mudabir. Okay, Mudabir, you're here, right?
Yeah.
1, 2, 3, 4, 5. Okay, I have all 5 of your answers. The pages are blue. I don't know why. Maybe it's the light. If you can fix that, please do that. But I can read it. It's okay.
Do you want me to resend it?
4, 5. It would be better if it's white. I don't know if there's a problem in your end or.
Oh, because my room's blue and the curtains.
Oh, okay. All right. It's not a big deal.
All right,
Okay, I got it. Michael Brosh.
Yeah, I'm here.
Okay, good. I have 1, 2, 3, 4, and 5. I have all 5 of your answers in separate sheets. You're good. Redwanu, are you here? Yes, you are. Okay.
Yeah, I'm here.
Good. Okay, so 1, 2, 3, 4, and 5. I have all 5 of your answers. You're also good.
Thank you.
You're welcome. Hasib Javed, you're here, right?
Yeah.
Okay. I have 1, 2, 3, 4, and 5. I have all 5 of your answers.
Thank you.
You're welcome. Haku, you here? No. Okay. Redwanul Haku, not here. Okay. Momina, Momina, you're here.
Yes, I'm here. Can you check if you see mine?
Okay. 1,
I sent it as PDF.
2, 3, 4, and 5. I have all 5 of yours. You're good.
Thank you.
You're welcome. Christina Cruz.
Here.
Okay. Okay. 1, 2, 3, 4, and 5. I have all 5 of your answers. You're also good. Arif, Sheik, are you here? Arif. Okay. Weizhen Zhao, are you here?
Yeah.
Okay, good. 2, 3, 4, 5. Wait.
Yeah, I missed one because I didn't have time to do that one.
Wait. What did you say? Number 1?
No, because I didn't have the time to finish that.
Okay, you didn't do number 1. That's why. Okay. I have all I have all your answers. 2, 3, 4, and 5 are all the answers you did, right?
Yeah.
Okay. Also, number 3 is sideways. For the next exam, have it right side up, but it's all right. Okay.
Sure.
For the final, though, make sure all the pages are like right side up. Okay, I have your whole exam. Okay, so for Ways and Zhao, I'm just gonna reply to your email. I'm just gonna say you only did problems 2 through 5. These are all of your answers. As confirmed on Zoom. Okay, so you don't have to reply to this. This is just kind of like, so I know that there is no problem. Okay. Okay, so next is David Cristobal.
Yeah, I'm here.
1, 2, 3, 4, and 5. I have all 5 of yours. You're good.
All right, thank you.
You're welcome. Maybe write in black in the future, but I can read it. It's fine. Jamil Abdin, are you there? Jamil? Nope. Okay. Oh, okay. So some of you are still here. You might want more review. Anyone here still want me to check whether or not I received their exam? I know I checked Saba, David, Momina. Aisha, did I check yours? I don't remember. Aisha? I guess I did. It's clicked. I'm assuming that meant I checked. Yeah?
Yeah. Okay.
Okay, I checked yours already. Momina, I checked yours. Saba, I checked yours. David, I checked yours. Hasib Javed, did I check yours already?
Yes.
I did. Right?
I'm here for the review. Can you do question 7?
Okay, yeah, but I checked your exam, right? You're good?
Yeah, I'm good.
Okay, that's what I'm just checking sure first. So Saba's good, Hasib good, Momina's good. G Lin, I checked yours also, I remember, right? So, okay, so I'm done checking whether or not I received exams. Okay, good. Let me quickly plug in my charger. That way I know that it doesn't run out of charge. So think about your questions about the final while I do this for 10 seconds. Okay, I'm back. Okay, good. Okay, so things maybe calm down now. Okay, which question do you want to ask about?
It was question 7.
7, sure. Okay, so 7 on the practice problem sheet. So number 7, 3 cards are dealt to a player from a standard 52 card deck. Find the probability he is dealt exactly 2 kings. Okay, so copy. So now we're going to look at number 7 from A. I'm just going to copy a little bit at a time here. Find the probability he is dealt exactly 2 kings. Okay, so that's the problem. He is dealt exactly 2 kings. Good. Okay. Wait. So I'm just going to be very particular here. 2 king, lowercase. Okay. All right. Okay. So solution. So 3 cards are dealt to a player from a standard 52 card deck. Find the probability he's dealt exactly 2 kings. So I changed the amount of cards the player gets here. So you get 3 cards, and you want exactly 2 kings. So the probability of being dealt exactly 2 kings is, let's think of the composition of this hand. You have 2 kings and 1 card that isn't a king, right? So I'm gonna let A equal the event of being dealt exactly 2 kings from a hand of 3 cards. Okay, you don't have to say that many words. I'm just doing it so it makes more sense. So this is equal to the probability of event A. And probability event A is the number of elements in the event A divided by the total number of sample points in the sample space, right? So usually the sample space is the easier thing to compute. So let's do that first, okay? So we have two steps. Step one is going to be to find the value of capital N. Step two is going to be find the value of N sub A. You know what, I'll just add an obvious next step. Step three will be plug the values of capital N and N sub A into the above to get the final answer. Okay, so those are our three steps. So first we're going to find the value of capital N. So remember, capital N is the number of sample points in the sample space, right? So let's think about what the sample space consists of. So let's think about what the sample space consists of. Okay, well, you're being dealt three cards, right? So the sample space is the set of all three cards that of all ways you can be dealt three cards from the standard 52 card deck. Okay, well, that means that capital N, which is capital N, is the number of ways to get three cards from the standard 52 card deck. And that is the number of ways to get three cards from the standard 52 card deck. The order doesn't matter, you're just getting any three cards. So there's 52 cards in the deck and you want three of them. And so that's equal to 52C3. I'm going to put that in a new line so it stands out. So does it make sense that capital N is 52C3? You have a set of all 52 cards in the deck and you want to just find the ways to choose three of them where order doesn't matter, right? When you're being dealt three cards from the deck and you look at your three cards, it doesn't matter what your first card, second card, and third card was, you just have three cards. Does that make sense?
Yes, it does.
That makes sense? Okay, good, right?
Yeah.
Remember we use combinations. We can use combinations, here because order does not matter in hand composition, right? So order doesn't matter. Now you could maybe use permutations, but then order would have to matter throughout, and then that would make the problem more difficult. The easiest way to do this problem, it depends on the problem. This problem is much easier using combinations because when you can just think, you don't have to start thinking about order. You can keep order not mattering. So capital N is 52C3, right? And so that's what you would plug in here. That's step 3, and I'm going to do part of step 3 now already. You see how that goes in the denominator for capital N, right? So for step 2, find the value of N sub A. N sub A is the number of sample points in the event A, right? So N sub A is the number of sample points in the event capital A. Well, what was the event capital A as we defined it? We defined A as being the event of being dealt exactly 2 kings from a hand of 3 cards. And so N sub A, which is number of sample points in the event A, is the number of ways to get a 3-card hand that consists of exactly 2 kings. Okay? And so how do you compute that? Well, the number of ways to have a 3-card hand with exactly 2 kings would be first, you look at the 52 cards and you have imagine 52 cards on the table spread out completely on the table so you can see all 52. Then imagine you want to take 2 of them. Oh wait, no, sorry. Imagine there are 52 cards in the deck, right? But you want to you look at the 52 cards. You see that there's 4 kings, right? So you have 4 kings, okay? And you want look at the 4 kings. Sorry, the king of hearts, king of spades, king of diamonds, king of clubs. Right? There's 4 kings, and imagine choosing 2 of them, right? So there's 4 kings on the table, and then imagine choosing any 2 of them. The 4 kings is a set, and you want to choose 2 of them for your hand. So there's 4C2 ways of, that's the number of ways to have 2 kings in the hand, the number of ways of choosing 2 of those 4. So 4C2 is the number of 2 kings you can have. And then if you have a 3-card hand that consists of exactly 2 kings, that means there's 1 hand that's not a king. And so then for the 3rd card, there's 4 cards in the hand that are kings. That means if there's 52 cards in total, there's 48 cards that are not a king. And so all you do now is forget about the 4 kings. Put the 48 cards that are not kings on the table, and you want to choose one of them. And so 48C1 is the number of ways to choose one of those 48 cards. That's equal to 48, right? 48C1. So you would probably just think of that without the notation, but I like the notation because you're using notation throughout the entire problem. Okay, so if you start calculating the number of ways each thing happens, you then have to look specifically at each situation, sub-situation of the problem. If everything's being done by combinations, every step is very easy. Okay, so that's equal to, well, 4C2, remember the formula, right? So the formula is that if you have NCR, right? If you have N, choose R. The N is not referring to this problem. And I kind of want to change the letters, but we use these letters in the formula. So I want to keep this one. So I'm changing the meaning of N and R here just for the formula, right? That makes sense. So N choose R is equal to N factorial divided by R factorial times N minus R factorial. That's the formula, right? And so that means that 4C2 is equal to 4 factorial divided by 2 factorial times 4 minus 2 factorial. Okay, and then this is times. But remember also a fact that NC1, when you use the formula that I just wrote above for NC1 will tell you that you have N factorial divided by 1 factorial times N minus 1 factorial. And that's equal to N factorial divided by N minus 1 factorial. N factorial divided by N minus 1 factorial is N. And so N choose 1 is equal to N. And I gave you justification there, right? So that means that 48C1 is 48. Okay, so that's immediately 48. And so 4 factorial over 2 factorial, this is 4 factorial divided by 2 factorial times 2 factorial. And that's also still times 48. Okay, and so 4 factorial is 24. That's 24 divided by 2 times 2, which is 4. And that's times 48. And so 24 divided by 4 is 6. And so 6 times 48. Okay, so that's 6 times 50 minus 12. And so that's 288. Okay, 240 plus 48, so it's 288. So N sub A is 288. And so then I'm doing step 3 already. So so the numerator is 288. Actually, I'm going to put this here. So the reason why I'm going to put this here is just so you can see how the entire problem can be done with just combinations, right? So I have the numerator as using combinations and the denominator as combinations. And then when you calculate that, you get. So if we go to the answers in the review problem, the probability of 2 kings is 0.013. Okay, and so 0.013. There you go. So you calculate that, you get 0.013. That makes sense?
Yeah, just to make sure I understand these questions properly, can I just change the question a little bit? So suppose if you were to get 3 cards and 2 of them were diamond, what would be the values only?
But you would say 3 cards and you want all 3 are diamonds?
2 of them to be diamond, right?
2 of them
So
to be diamonds. Okay, so
we take
separate
13 to, right?
similar question to 7. Okay, so the question is, what is the probability of getting, you're saying exactly 2 diamonds in a 3 card hand from a standard 52 card deck? That's your question?
Yes.
Okay. Okay, so this is not a review sheet, it's just a side question. What's the probability of getting exactly 2 diamonds in a 3 card hand from a standard 52 card deck? Okay, so let's think about what's happening here. Well, actually, first let's make some notation. So I'm gonna let B equal the events of getting exactly 2 diamonds in a 3 card hand. Okay. So that means that the goal is to find the probability of B, right? Probability B is probably event of getting exactly 2 diamonds in a 3 card hand. That's equal to n sub B divided by capital N. So you see how that's automatic?
Yes. I
Right,
do understand.
so-
I do understand the answer. I just want to see if what would be the values, by the way, like.
Right, I'm not, so I'm gonna explain everything, but I think you're implying that this doesn't matter, right? So this matters.
No.
So
Okay.
if
yeah.
B is the event of, if you let the event be the thing you're trying to find, then by the formula is going to help you get the answer, because the probability of this event B is equal to n sub B over n, where n sub B is the number of sample points in the event B, right? And the number of sample points in the event B is the number of 3 card hands that consist of exactly 2 diamonds. So by using the notation, right? The notation is in a way leading you towards the answer without knowing how to get the answer. You don't know how to get the answer, but by writing a notation down, the notation is telling you, in a sense, where steering you towards the answer. Does that kind of make sense? Okay, so if you let B be the event of it getting exactly 2 diamonds in a 3 card hand, first you see, okay, that's the thing I'm thinking about. This is the event. P of B, that's the probability of the thing. That's what I want to find. That equals to n sub B over n. N sub B is the number of sample points in the event B. That's equal to the number of 3 card hands that consist of exactly 2 diamonds. So you see how already it's becoming more clear what you need to find?
Yes.
So the better you understand what you need to find, the easier it is to get what you want, right? If you want to get something, knowing what you want makes things easier, right? You want the number of 3 card hands that consists of exactly 2 diamonds. That's n sub B. And you also want capital N, right? Capital N is the number of sample points in the sample space. That's just the meaning of capital N. Capital N is always the number of sample points in the sample space of your experiment. Well, then you ask, okay, what is the sample space of this experiment? Well, you're getting 3 card hands, right? You're finding the probability of a specific 3 card hand, but the sample space consists of 3 card hands. So capital N is the number of 3 card hands from a standard 52 card deck. Does that make sense?
Yes.
Okay. One of the problems would be like, what is n sub B and what is n, right? That's your question. But in order to know the values of n sub B and n, you have to understand what they mean, right? And n is sometimes difficult because capital N can be easy to compute, but it might be hard to understand what capital N represents, right? Because you
Yeah.
have 3 cards in hand, but then you also have 2 diamonds. And so well, very often, capital N can be confusing to understand, but easy to calculate. So using the notation, it's helping you understand what N is. Once you understand what N is, it might be very easy to calculate. So capital N is the number of sample points in the sample space. That equals the number of 3 card hands from a standard 52 card deck. So now, just using the notation, can you tell me what capital N is?
Using the notation, capital N is supposed to be 52, right?
Sorry?
52, right?
Can you say one time what you said?
Just 1 second, sorry. It's 52, right?
You're saying it's 52?
Yeah.
Imagine this, okay? Imagine in your mind that you have a table and you put all 52 cards in the standard 52 card deck on the table, okay? Are you imagining that?
Yeah.
Okay. Now, what you want a 3 card hand, right?
Yeah.
So what do you want to do? You want to choose 3 of those cards, right?
Yeah.
What's the notation for the thing that if you have a set of 52 objects and you want to choose 3 of them, the notation that tells you the amount of ways to do that?
3 choose 5, 52.
What is it?
3 choose 52.
52 choose 3.
Oh yeah, sorry, my bad. Yeah,
That's okay. Does that make sense?
it does.
That notation, there's a formula, right? And the formula tells you the value of that symbol, right? But what that symbol says, 52C3, it's the notation that denotes the number of ways, if you have a set of 52 distinct objects, the number of ways that you could choose 3 of them, or it doesn't matter. You just choose any 3 of them. Does that make sense?
Yeah.
And so in this
It does.
problem, you have 52 cards, and to get a 3 card hand, you just want to select any 3 of them. Order doesn't matter, right? Just the number of ways you can have 3 of those 52 cards. That's 52C3. That make sense?
Yes.
So you see how using notation means without making calculations, you're getting to the solution.
Yeah.
Right? The final step is calculating these values with formulas, right? But that's like the uninteresting part, right? Calculating these values is uninteresting. You're just using a formula, right? But then, finding the notation to represent your answer, that's the whole problem. Okay, so you have 52C3. That's N, and that makes sense, right? You're saying that makes sense, 52C3?
Yeah.
Okay, now N sub B is the number of 3 card hands that consists of exactly 2 diamonds, okay? So how many diamonds do you want, and how many non-diamonds do you want?
2 diamonds and 1 non-diamond.
Good, so let's look at 2 diamonds. You want exactly 2 diamonds. How many cards in the deck are diamonds?
13.
How many?
13.
13, right? Imagine those 13 cards are on the table. Only diamonds. All the diamonds in the deck are on the table. 13 diamond cards. Okay, how many of them do you want?
Only 2.
You want 2, right? How many ways are there to choose 2 of them?
13 choose 2.
Yeah, 13C2. Does that make sense?
Yeah.
And forget about what you need to know to calculate this, but don't think for a moment about how you would calculate that value. Just think about the fact that 13C2 is the notation for the number of ways where if you have 13 things, choose 2 of them, right?
Yeah.
So you see, N sub B is not a probability, it's a number, right? We're calculating the number of ways to have 3 cards. You have 52 card deck, the number of ways to select 3 cards in which exactly 2 of them are diamonds. Okay, so we have the number of ways to choose exactly 2 diamonds. Now, imagine, so how many cards do you need that are not diamonds?
Only 1.
Good. Now, imagine taking those 13 diamond cards and just throwing them on the floor, okay? Now, take all the other cards in the deck and put them on the table. Okay, you imagine that?
Oh yeah, it's 39 choose 1, right?
Yeah, exactly. There are 39 other cards in the deck that are not diamond. So those are the only cards you care about. All the other ones are on the floor. They don't matter. So you have the 39 cards that are not diamonds, and you want to choose 1 of them. And do you see how you would multiply the two?
Yeah.
Right? If you want an outfit and you want a pair of pants and a shirt, and you have two choices for pants and two choices for shirt, the number of ways to make each choice would be 2 times 2, right?
Yeah.
You'd have 2 pants times 2 shirts. You'd have 4 outfits, right? Here, you have 13C2 ways to have exactly 2 diamonds, and you have 39C1 ways to have exactly 1 non-diamond. So the number of ways to have 2 diamonds and 1 non-diamond is 13C2 times 39C1. Does that make sense?
Yeah.
So
Really good.
now together, 13C2 times 39C1 is the number of ways to get 3 cards from the standard 52 card deck where exactly 2 of them are diamonds and 1 isn't, meaning that there are exactly 2 diamonds in the 3 cards. Make sense?
Yeah.
Okay, there you go. So that's n sub b and n. And so now you just take n sub b as your numerator. And you take n, which is 52C3 in your denominator. Does that make sense?
Yeah.
Okay, and then you just calculate each of them. So for instance, 53C2 would be 52. I'm going to use the times symbol. 52 times 51 times 50 divided by 3 factorial, which is, all right, 3 factorial. Okay, that's that one. This is the same as, well, the first one is 13 times 12. I'm using the shortcut for calculating it. Right? Does that make sense? Divided by 2 factorial. And then this is times the other 39C1 is 39 by the shortcut I said earlier. Okay, so you have each of those. 2 factorial is 2. 12 divided by 2 is 6. 6 times 13 is 78. So you have 78 times 39. I could do that in my head, but I just want to make sure I have the right answer. 78 times 39, and that's 3,042. So you have 3,042 because you have 78 times 39. 78 times 39. There you go. Okay, and then this one, you have this. So 52 times 51 times 50, and then divided by 6. And so this is 22,100. So now this is equal to the numerator. The numerator, which is this product, is the same as 3,042. And the denominator is capital N, which is 52C3. That's 22,100. Okay, so this is equal to 3,042 divided by 22,100. And that's equal to 0.1376. So it's the 4 decimal places on the exam. And so I rounded that to 4 decimal places. The next decimal place is a 4. And so it's 0.13764, so forth. And so that rounds down to the nearest 4 decimal places at 0.1376. 0.1376. That make sense?
Yes, yes. I have
Okay.
another question.
Okay.
Okay, I'll just send it in the chat. It's not from the document.
Okay,
I
what?
have a quick question. Can I ask that first?
Well, you know
Yeah,
what?
sure.
Let's take turns. So what's your question?
So like my question is related to this 2 examples. So I get confused when to choose the suit and when to not. So like from the examples that I have seen a pattern is like if the suit is mentioned specifically, then we don't do 4 choose 1. But like I'm assuming if the suit is not mentioned specifically, like for example, if it says like if the 2 cards from a 3 card is of a 1 suit and other is from any other suit, then we would do 4 choose 1, right? To choose the suit.
Okay, I was having trouble understanding. Just the question. You want to say if you have 52 card deck and you want 4 cards?
No, I think like because sometimes we do 4 choose 1 to for like to choose the suit of the card, right? Like to choose 1 suit out of the 4 suits.
Oh, right. Okay, I think I know what you're saying. So like for a flush, right?
Yeah.
If you want to find the probability of a flush, right? Then so another question, right? Okay, so explanation of something. Okay, so if you have the probability, if you have F is a flush, right? Okay, so if you have F is the event of the flush, right? A flush means that you have a 5-card poker hand consisting of all same suit, right? Okay, so I think this might lead to helping you with your question. So the probability of that event F would equal to the number of cards in a flush divided by the total number of cards in the deck. That's equal to, right? So you would find the values of N sub F and N. So N sub F is the number of flushes, which is the number of 5-card poker hands consisting of all the same suit. And so this relates to your question, I think, because to find a number of flushes, you would think about the process in which you would get a flush. Okay, so sometimes you think about the process you would use to get a flush, and then you would calculate the number of ways that you would do each step in that process. And when you multiply them, in total, you get the number of ways of getting a flush. So for instance, to get a flush, certain things have to happen. 1, every card is the same suit. And then 2, you have to choose the right number from that suit, right? So a flush is 5 cards. A poker hand is 5 cards. A flush is in poker, so you have a 5-card hand where every card is the same suit. So this process is going to have 2 steps. Step 1, imagine you choose a suit, okay? So what are the number of ways of choosing a suit?
Or choose one.
Good, very good. So 4 choose 1 is the number of ways to choose a suit. Okay, now that you've chosen the suit, whatever it is, imagine putting all the cards of that suit on the table, okay? Whatever particular suit you chose. Imagining that?
Mm-hmm.
Okay, so now you want 5 cards from that suit to build your flush. So you agree with me that if you first choose a suit and then you choose 5 of the 13 cards of that suit, you now have a flush?
Yes.
And do you see that not only is every time you do this a flush, it exhausts all possible ways to get a flush?
Right.
And you see that each different choice would be a different flush. So there's a 1-to-1 correspondence between all the number of ways to do this process and the total number of flushes. So to count the number of ways to first choose a suit and then to choose 5 cards from that suit is the same as counting the exact number of flushes. Does that make sense?
Yeah, I get that.
Okay, good.
Because
So
you
how many
have like
ways can you?
options of choosing the suit, right? Yeah.
So how many ways can you choose 5 of the 13?
13 to 5.
Exactly. And so then, just like the outfit example, you would then multiply those 2 values. So 4C1 times 13C5 is the number of ways to first choose a suit, then 5 cards of that suit. And so the product is the number of 5-card flushes. Does that make sense?
Yes. Right.
Okay, so
Thank you so
4C1 is immediately 4 by the previous fact. And then 13C5 is then 13 times 12 times 11 times 10 times 9 divided by 5 factorial. Make sense?
Yes.
Okay, so 5 factorial is 120. And so 12 times 10 is 120. And so it's 13 times 11 times 9. 11 times 9 is 99. So it's 13 times 100 minus 13. So that's 1300 minus 13. So that's 1287. So it's 1287 times 4. So 1287 times 4. So that's 1287 times 4. So 1200 times 4 is 4800. And then 87 times 4 would be 360 minus 12. So that's 348. So this is 51 5,148. I'm going to check that. Hold on. Okay, so you have 13 times 12 times 11 times 10 times 9 times 4 divided by 5 divided by, now I gotta redo this. Hold on. 4 times 13 times 12 times 11 times 10 times 9 divided by 5 divided by 4 divided by 3 divided by 2, 5,140. Yep, that's it. Okay, good. That makes sense? Does
Yes, thank you.
that answer your question?
Yeah.
Okay, good. So when something's not clear, if something doesn't make sense, the best way to understand it is through examples. So if you're studying on your own and a concept doesn't make sense, try to come up with it, try to have an example that closely matches with the thing you don't understand. So by solving the example, you're figuring out how that thing. Does that make sense? So examples and problems are the best way to study. So you should be doing problems and examples to study for the exam. Okay, other questions?
I have a question. I sent in the
Yeah.
chat.
Hasib? Yeah.
Yeah, I sent in the chat the question.
Oh, okay. Consider the experiment of a single non-repeating die. What? And a single toss of 2. You mean a 6-sided fair die?
Yeah, my bad. Yeah.
All right, no problem. Consider the experiment of a fair 6-sided die and a single toss of. Wait, do you mean tossing a coin twice, or do you mean one coin with 2 sides?
I just got this from your previous exam, and since you do not like to open any uploaded photo, that's why I just typed it out. I can share my screen to show you the question.
No, it's okay. This is one of my problems? I don't think so. Is it?
Yeah, it's like a year ago. Yeah.
Okay, it's not in this class though.
No, not in this class. Yeah.
Oh, okay, but whatever. Okay, so you have the experiment of a single dot 1 through 6, and so you want to toss 2 coins. Okay, the x1 be the value in the die, and x2 be the number of tails. Okay. Find the joint probability function of x1, x2. Okay, so this is a side question. Okay, so if a problem was in another class and it didn't show up here, this is a side question that doesn't necessarily reflect the exam. Okay, so side question. So let's capital A equal the events of forget about events for a second. So I guess I'm going to copy and paste the problem. That's what I want to do. And then reword it. Consider the experiment of a single of tossing a fair 6-sided die once, and then flipping coin twice. Let x1 be the value on the die, and let x2 be the number of tails from the. I'm just going to make this clear, from the 2 coin flips. Find the joint probability function of x1 and x2. Okay, solution. Okay, so so we want to find f of x1 and f of x2. Okay, so f of x1 is the probability function of capital X1. And so the value on the die, well, it's 1/6 for x1 equaling to 1, 2, 3, 4, 5, or 6. Does that make sense?
Yeah.
Okay. And then f of x2 is the probability function for capital X2. And so x2 is the number of tails from the 2 coin flips. There's nothing wrong with that, I don't think. Okay, so f of x2 is the number of tails from 2 coin flips. So on the whiteboard, I'm just going to illustrate this, and I'm going to label this as a side question. It's not a question on the exam. Okay, so if you flip a coin twice, right? You could either have heads, 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 tails, tails, heads, or tails, tails, right? And so those are the 4 ways to flip a coin twice. Now x2 is the number of tails from 2 coin flips. So find the joint probability function of x1 and x2. So x2 is a random variable, and x2 as a random variable is a function where the input of the function is a sample point, right? Is a sample point in your sample space. And the output is a number, it's a real number. Okay. So so when as x2 as x2 of h comma h, which means ahead in the first and second coin flips, in this case x2 is the number of tails. Wait, number of heads or tails? Check again. Oh, where are we?
Number of tails. Oh.
Hold on. Oh. Here we go. Okay. X2 is the number of tails. Okay, good. X2 is the number of tails. So X2 is the number of tails. So that's 0, right? Does that make sense?
Yeah.
X2 of HT is equal to 1, because there's 1 heads there. X2 is a function where the input is the sample point t comma h. First flip is a tails, second flip is a heads. The number of tails then is 1. And then x2 of the sample point t comma t. First flip is tails, second flip is also tails. The number of tails is 2. You see how x2 is as a random variable is a function where the input is each sample point and the output is a real number?
Yeah.
Okay, well, then what is f? So my question for you is, what is f of x sub 2? Wait, it's the number of tails. Okay, so f of x sub 2. So first, is f of x sub 2. Now, what I want to also point out are what are the possible values of x sub 2, right? X sub 2, can you tell me what are the possible values of x sub 2?
It's 0, 1, and 2.
Good, right? These are all the values of x sub 2.
So
So
we
x
read
sub 2,
one
x sub
twice.
2 is either 0, 1, or 2. Sorry, I just want to finish my thing here. So f of x sub 2 would be f, the probability that capital X2 takes on one of these values. And so you would want the probability when x2 is 0. You would want the probability of f of x2 when x2 is 1. And you would want the probability of f of x sub 2 when x2 is 2. Does that make sense?
Yeah.
Okay, so what is f of 0?
F of 0 is head and head.
No, so f of 0 is the probability that the value of x sub 2 is 0. Okay.
Oh, it's 1 over 4.
Was it?
1 over 4.
Good. Okay, so keep in mind that not only is the likelihood of getting heads and tails the same, they're both 1/2, but they're both the same, the likelihood of each choice of 2 sides is the same. So heads is as likely as heads tails, which is likely as tails heads, which is likely as tails tails. Does that make sense?
Yeah. Yeah.
Okay, so there's only 4 ways you can have, you know, you could flip a coin twice, but each of those 4 ways has the same likelihood of occurring. And so since they each have the same likelihood of occurring, you can just count the number of ways there are 0 tails in 2 coin flips and divide that by the number of ways to flip the coin twice. Does that make sense?
Can you say it again?
So
Sorry.
do you see how there's only one way that there are 0 tails
Yeah. Yeah.
out of the total 4?
Yeah.
Right? But there's no weight. The likelihood of getting heads and tails is the same as heads, and it's the same as tails, heads, and the same as tails, tails. So we don't have to weight the likelihood of 0 tails to be more or less than the likelihood of these other ones. Does that make sense?
Yes.
So if one of those 4 were more or less likely, you couldn't do 1/4, but we can here because all 4 ways to flip a coin twice is equally likely to happen. Does that make sense?
Yeah.
Okay, so 1/4 is the probability that x2 takes on the value of 0. What is f of 1?
1/2.
Good, right? Because it's 2/4, which is 1/2. And what is f of 2?
1/4.
Good. And so now f of x of 2 is that. You can even simplify this to say it's 1/4 of x2 is 0, 2, but I'm just going to do this so that it's clear. Okay, so that's the probability function f of x of 2. Okay, so let's go back to the whiteboard and keep note that we now found f of x of 2. Okay, so f of x of 2 is equal to f of x of 2 is equal to 1/4 if x of 2 is equal to 0 or 2, and it's equal to 1/2 for x of 2 equaling to 1. Right? Make sense?
Yeah.
Okay, let me just check. X of 2 is 1. X of 2 is 1, 1/2. X of 2 is 0 or 2, 1/4. Good. 0, 2, 1/4. Okay, so now that's our probability. Now, the act of rolling a die once and then flipping a coin twice is an example of when 2 experiments are independent. When 2 random variables are independent. Okay, so here the events x1 and x2 are independent. I mean, here are the random variables. X1 and x2 are independent. Does that make sense?
Yes.
Right? When you have 2 things that happen and they have no effect on the outcome of each other, you can take their separate random variables and think of them as independent. And so the consequence of that is that f of x1 comma x2, the joint probability function of x1 and x2, the probability that capital X1 is equal to little x1 and capital X2 equals little x2, well, that's equal to f of x1 times f of x2. That makes sense?
Yeah.
Okay, wait, so this means, if that's not clear, this means that the probability of x1 equaling little x1 and x2 equaling little x2 is equal to the probability that capital X1 equals little x1 times the probability that x2 is equal to little x2. That make sense?
Yeah.
The probability of 2 things both happening is equal to probably the one thing happening times the other one. like an outfit. Like if you make an outfit where you choose 1 out of 2 pair of pants and 1 out of 2 pairs of shirt, you choose 1 out of 2 pants and 1 out of 2 shirts. The number of outfits is 2 times 2, which is 4. The way you choose, maybe sometimes it does, but I'm not caring here. The way you choose the pants, I'm saying, has nothing to do with how you choose a shirt. And so you just multiply, right? But it's similar, except with probability. Okay, it's not exactly that, but you would say the probability of 2 things happening is probably of 1 thing times the other when they're independent, right? So the fact that these 2 are independent random variables means f of x1 comma x2 is equal to f of x1 times f of x2, because what that's saying is the probability of 2 things happening is a product of the respective probabilities. Does that make sense?
Yeah, right. Yeah.
This notation, f of x1 comma x2, is that probability. And f of x1 is this probability, and f of x2 is this probability. So saying the probability of 2 things happening is the product of the respective probabilities. Okay, so now that's equal to, so we now found this, right? So this is going to be a piecewise function where, first off, f of x1 is always 1/6, right? And so there's only 2 possibilities of those depending on what x2 is, right? So if x2 is 0 or 2, then you have 1/6, which is the probability of f of x1, times 1/4, which is f of x2. And that's equal to 1 over 24. And this is if x2 equals 0 or 2. And also x1 can take any of the values, 1, 2, 3, 4, 5, or 6. Okay, that's for each of them. So for instance, for each x1 you choose and each x2 you choose, that's the probability f of x1, x2. So there's really 12 ways this could happen. Does that make sense? So there's
Yeah.
12 different choices of x1, x2, which have a probability of 1 over 24 from happening.
Yeah.
Okay, good. Okay, and then if x2 is equal to, oh wait, so x2 has to equal 2 here. You see that from here?
Yeah.
Right, okay. Now, if x2 is equal to 1, then you have still 1/6 for f of x1 times f of x2, which is 1/2. And that product is 1/12. And this is if x sub 2 is equal to 1, and still x1 can take any value. So I'm just writing it down. This way it just makes sense. Perhaps writing more than I have to. And does that make sense?
Yeah, yeah.
Okay, and so that to
Yeah, I understand
elaborate
it.
what I mean by this means that f of x1 comma x2 equals f of x1 times f of x1 means that, okay? And this is a note. This is not needed in the problem. Note that equation means that those 2 things are equal, okay? And so this is the answer. And so now we are done. Make sense?
Yeah, thank you very much, Professor. Sorry for
You're
taking
welcome.
like
Okay, so we'll
30,
stop
40
the
minutes.
review there. Okay, and so good luck on the final. I'll see you on Monday.
All right, thank you very much.
You're welcome. Bye. A whiteboard. Save the whiteboard. Save as PDF.